Hello everybody, welcome to the EUPAVE webinar on optimal compaction for a durable concrete surface. My name is Luc Rens. I am Managing Director of EUPAVE and your moderator for this webinar. Let me start with a brief introduction. Probably most of you all know what EUPAVE is, the European Concrete Paving Association. We were created at the end of 2007, so we're about 15 years old. And our mission is to advocate and enable wider use of cement and concrete applications in European transport infrastructure. How do we do that? Well, we want to engage with our important stakeholders, with people from the European institutes, but we also want to disseminate technical know-how, communicate on the benefits, and we want to promote innovation and best practices in the sector. Well, that's exactly what we want to do today. Our main activities are roads and safety barriers, but you can see in the list there are many other applications we deal with. We have members and we have partners. Members are either full or associate members, mostly national, international cement and concrete associations, associations of contractors and equipment manufacturers. Our partners are mainly contractors and consultants and designers. Most of the work of EUPAVE is done in our working groups. As you can see here, we have 6 working groups. Best practices, that's the one in charge today. To exchange know-how, best practices between, amongst us, amongst members and partners, and also with you today. Environmental Strategy Working Group, we have been producing a large number of fact sheets in recent years. The EU Advocacy Group, which deals with kind of lobbying and communication at the EU level. Concrete Safety Barriers Working Group, Concrete Pavement Statistics, and also Communication Tools Working Groups. So, for those who are not yet a member or a partner, you can always ask for information or you can find it on our website. We would also like you to join EUPAVE as a member or a partner. So, dissemination of best practices and know-how is one of our key objectives. That's why every year we organize a workshop on best practices. As you can see here in the list, in the past we've been talking about evenness, joints, the concrete mix, base layers and roller compacted concrete, concrete pavement preservation, pervious concrete pavements. And here I already can announce you that in 1 month we'll have our next best practices workshop. It will be in a hybrid form. And it's about outdoor, industrial and heavy-duty concrete pavements. So already note the date, 19 April 2023. And also webinars have been organized, as you can see, from 2019 on. So we already started just before COVID. And this is the 5th one we are organizing today. Optimal compaction for a durable concrete surface. So the objective is today is to learn why compaction is important for good construction of a concrete pavement. Well, compaction is one of the elements of the processing of fresh concrete. First we start mixing at the plant, we transport it from the plant to the site, concrete is poured, and then it should be compacted. Afterwards, it has to be protected from drying out of the concrete surface. Now, we talk about optimal compaction. It means there can be an insufficient compaction, which may lead to problems, as you can see here on this figure, entrapped air or aggregates and reinforcement which is not covered, air bubbles along the formwork or in the corners. But it's also possible that the compaction is too intensive and that may lead to segregation of the concrete, and one of the possible consequences are the vibratal trails that you can see here on this photo. I'm not going to say more about this because today we have 3 excellent speakers. 3 speakers together way over 100 years of experience, I think closer to 120 years of experience for the 3 experts that we have invited today. And the first one is Mr. Paul Jaworski. He's product manager for Minnich Manufacturing. Minnich Manufacturing is a US company which manufactures vibrators and also dowel pin drilling equipment. So, I give now the floor to Paul for his presentation. Thank you.
Hello, I'm Paul Jaworski. I'm with the Minnich Manufacturing Company. I'm their product manager, and welcome to the EUPAVE webinar. Thank you for tuning in. We have 3 presenters today, and I'll be talking about the applied vibration against concrete mechanical resistance and what its impact is on carbon neutrality. I'm going to stick to, in my 20 minutes, more of how it plays a role, or the measurements of controlled vibration, and how it plays a role in design and other factors that come along with the concrete workability system. The vibration energy's impact became very obvious as we started working with researchers that we had to understand and be able to measure vibration energy and its mechanical resistance, and this critical step out of developing sustainable field practices. So we set controlled frequency, and it allows for the measurement of applied vibration energy into the plastic concrete, because that's the only place that it's really important. When vibration is controlled in the paving process, it's made to be a constant. You can throw it away. You don't have to worry about that being variable. And then when you start looking at where's my other variability coming from, and that variability is understanding, measuring the whole workability system. And so when we look at design, we look at what's in the concrete, what are its properties, what its performance targets, and we hope that it actually turns out that what gets put down in front of our vibrator has some of the same metrics for workability that were designed or expected in the laboratory. So once it gets out of the laboratory, it's batched there. It could go through a trial batch period, and then we look at what happens with batching, what happens with water additions, how much high-range water reducing agents are used, what's the material moisture, are we controlling it, are we getting it from a concrete truck, are we getting it from a dump truck, are we having slump loss, and in this instance, unless we're looking at bridge decking, it won't be pumped, but there is some slump loss between what this target is to what happened in transit to what got delivered to the paving machine, and even how far away from being run over by the paving machine was the concrete sitting there. In order to do that, we began to look at controlling vibrators and taking the actual energy that we apply to the workability system, or what the mechanical resistance is of the concrete, and just focused on changes in that resistance, so we can match the two. When we look at variability in batching, we look at, well, here is a tarantula curve, and I'm sure that Mike in the next segment will be talking about it. But as we look at batch at batch, these are all lines that are from batches, and they begin to start walking outside of that curve as we look at each batch that's delivered to the job. So we can go back and maybe we can begin to look at how's my vibration that's fixed matching up to changes in the concrete resistivity. And if we measure it, we can kind of figure when that resistivity is changing, and then we look at what the sources are of the variability. Batch variance we look at from the aspect of uniformity, and uniformity can be in a couple of directions of what is actually coming out of the drum and slump, or out of the truck, and what's coming out of it as far as what the break strength deviations are. And it tells us pretty much a lot about where the uniformity is, and there's a lot of savings in the actual measurement of what the workability is. Paste volume is really important to vibration, and it's kind of obvious. If you are trying to put this volume of cement into this void spacing from gradation, no matter how much you vibrate it, you're still going to have these pockets of air that are caused by bridging, and they show up in several ways, and we'll look at one of those because it's a common occurrence, and with machine operators, it's a common adjustment that gets us into a little bit of trouble. But it pretty much makes sense that the paste volume should be larger than the volume of voids, because you have to cover the particles. Now, that is something that I usually take my cues from people that are a lot smarter than me in developing strength in concrete pavements, and how much paste it takes. I know that looking at optimization, these little windows right here become a little bit tighter, and if we get a little out of whack with how much volume that we actually put into it, we'll have some issues that are really design issues in the workability system that are going to be very difficult to overcome. And a lot of time it's just a matter of putting more vibration speed to get more paste volume up to the surface, and it's a practice that we've been recognized as needing to be limited. When you don't have enough, this is about 90% of the issues, when we have these rock pockets that are on the surface of the pavement, the large amount of probability of why they're there is exactly what we just talked about in the last slide, which is there enough paste to actually fill the void spaces that are part of the gradation system, or the volume of voids. High vibrator frequency, because of these little voids that show up on the surface, will help with the finishing. There's no two ways about it. The speed will bring some cream to the top so we can get it finished, but it causes increased permeability, as we've done in the study, air entrainment reduction, for freeze-thaw durability, poor aggregate arrangement, which can cause some surface crackings under certain conditions. And also, more in the use phase of carbon neutrality is poor IRIs, that it takes, the rougher the road, the more fuel is consumed by the automobile. So as we look at how everything fits into the workability system from design to dropped in front of the paving machine, and it's always about understanding, controlling, and measuring the balance of applied vibrator energy and the mechanical resistance of concrete, being able to measure the two. Vibration is really very simple when we look at it, because now we just take measurements. It's not linear mathematics. It's not a bunch of wives' tales. It's not best practices. It's controlled. You're putting in P waves and S waves coming from the same vibrator head. The harmonic pressure coming from the P waves is moving harmonically, or extruding concrete out the back of the paving machine, while the S waves excites the available water, and that works as a lubricant so you can extrude the concrete out. So frequency is allowing for that lubrication, as the off-center weight, or how much force you're putting into it, and the harmonic pressure is actually doing the extruding and the consolidating. The frequency effect needs to be somewhere in the ballpark of balance with the dampening effect of the concrete, or the angular friction, how much frequency can it actually take as the water's excited, and then when it goes past that, when the frequency passes the dampening effect of the concrete, and it has a tendency to separate material. And in this case, we're talking about water. Okay. The vibration energy is not hard to figure out. We have a vibrator that is somewhere between 200 and 400 Gs. They're more closer to 400 Gs on paving machines. It puts out a force value at a VPM, and that puts out 3 Gs to or greater to how far away is its radius of action by the mechanical resistance of the concrete or working against it. And this is we just measure it. We don't have to worry about what the radius of action or spacing, and we just take a measurement. We know it's 200 Gs, and we take an accelerometer and we measure it. And it helps us with understanding what the mechanical resistance of the concrete and what's workable. As far as what off-center weights or at what frequency are you putting an X amount of G forces into the concrete, we kind of settled in on the right balance between off-centered weights and at what frequencies. And they used to run at much higher frequencies, but as we did the research and matching, as the years went on, we slowly moved towards maintaining certain speeds to get the right amount of G forces to match how far away the vibrators were spaced, and how much the concrete and the vibration resistance and the vibration matched, so we didn't get some of the material separation that we used to get with some of the mismatched frequency versus concrete resistivity. How much in a cubic foot of concrete is still something that databases need to be built, so we can look at it, at what exactly transpired. When we look at a paving machine, it's moving horizontally through a cubic foot of concrete, or in this case, roughly a third of a meter. And commercial is a little bit different. We're 3 seconds in a cubic meter, so we move in and out of that third of a cubic meter much faster in vertical than we do when we're doing pavements. We're dragging that thing along at hopefully a consistent pace. But if you're if you're looking at the machine travel speed of it, if you're going roughly a third of a meter per minute, that's 20 seconds of a cubic foot that you're putting vibration into. So we kind of have a tendency to do a little bit on the over vibration side of it, and it's something that you can look at by looking at what you're measuring, the resistivity of your concrete, and getting more data built on what this travel speed means to the outcome of your the uniformity of your pavement. How do we look at this stuff? Well, it's nice to talk about measurements. Well, how are we actually doing it? How vibration energy is weighed against mix efficiencies. Basically, if you control your vibration, it has an impact on your mix, and sometimes you can get more efficiencies out of that mix if you don't have to put more micro air in it because vibration is taking it out, or paste because you're having paste issues, volume issues. So getting those in sync, getting vibration frequency and energy in sync with what the resistance of the concrete is really important. And that's why we always preach, and what we work for in carbon neutrality is measure the vibration and measure the concrete mechanical resistance. And how do we measure it now? Well, we just had a celebration at ACI, 1911 to 2021. That it's actually been 100 years of the slump cone test. Abrams was a smart guy, and we use that. Our language is in slump, but it's not used very much in the United States as far as looking at what the mechanical resistivity of the concrete is. We're still pretty much haven't done anything with Mr. 1928 break strengths. And we've done some vast improvements on actually looking at the pressure pot test for evaluating the health of the micro-wear system for freeze-thaw durability. But we've been on the concrete workability measurement bandwagon with looking at revising the V. Kelly, making it a little bit mobile, and we've been doing this mostly for testing. It's made for concrete pavements, and really the scale for the V. Kelly goes past the 0 mark to almost solid or solid. And the angular friction, we stop with a cone, we stop right here at 0, and there's a lot more to on the left-hand side of the scale that we don't look in negative numbers. Looking at it as in inches is the language of workability, in slump is in inches. And we've been looking at just the values in the V. Kelly on getting a accurate indexing system that is repeatable, very repeatable. And that's the most important thing. And so, yes, we made it more portable. You could take it apart. I'm probably familiar with how the V. Kelly works and the ball dropping in the concrete, and it's measured by scale and time, and it's put into a Excel file, and that angle, that slope is calculated. As part of the V. Kelly indexing system or measuring system, it has a motor with a ball on the end of it. And as that ball sinks, we get a nice flow line right here that has a voltage assigned to it, how much voltage it took, or resistance against the ball. And here's basically where slump cones is in the static portion of shear stress, and the dynamic shear stress shows us, just exactly what that flow line looks like, and it's pretty consistent, and it fits the being a model for dynamic yield stress. So that's why we kind of go towards that V. Kelly measurement, because it's got, we're in that concrete and this is time down here, we're in that concrete for a long period of time. So it gives you a lot of data. And so we look at that data and what it takes to keep that extrusion process or that flow of concrete going with vibration. And we can look at changes in that vibration and look at that flow line to see what those differences are. Another piece of destructive testing is resistivity testing. It's not non-destructive yet. We're looking at pore development, and that pore development comes from if you look at some higher frequencies and you move some water up to the top on finishing, it has a tendency to leave a little bit of a capillary system near the surface, or these pores, and we kind of want to stay away from that, especially in the northern section of where I come from, that they use a lot of chlorides to de-ice. One of the other methods has been looking at, and I'll show you a slide on it. He's been the Oklahoma State University, and they look at very closely. They look at how much the vibration is transferring through the material. Now they use a compatibility test for vibration called the box test. They put a vibrator into a box. They run it for 3 seconds and then they strip it and they see exactly what this surface is like and does it take to vibration, and they kind of quantified that vibration so they know that when they strip it, they got something that's representative of what it's going to have as far as energy-wise on the surface. And they do other experiments too on vibration transfers, and we'll talk a little bit about transfers versus some of the resistivity readings that we can take. And this is our friends at CP Tech Center, Dr. Taylor. We use a box with accelerometer, and we can take some pretty good readings. We put a vibrator on the left-hand side of the box, and these are energy transfers, and there's 3 probes down there from the top of the vibrator to the, and you're looking at time, and time is very interesting to evaluate concrete by, because the more angular friction resistance, the longer it takes for this to go through. So you can look at it from that flow curve you saw on the last 2 slides ago, looking at that dynamic flow curve, or you can look at it just from what the speed of the energy is as it goes from 0 to I think 20 seconds, and hard to see, but it's telling you something about the actual value of the concrete resistivity. And part of what we look at, what the void spacing is, and it's stuff that we look at just to make sure that there's no scaling, to make sure that there's other things, and some of them are surface driven, that there's other things that we want to make sure that we don't do to the concrete, and this is basically for freeze-thaw durability. But again, we look at flow lines, and we also, in the testing, we compare them. And this one's a rapid air test, and it's basically saying that where I have the vibrator at, I'm reducing air, and I have higher air content farther away from the vibrator, and that's not macro air. It's not because we haven't consolidated it. It's because we've taken this air and it collates under vibration frequency, and then it finally gets buoyant and starts moving away from the vibrator as it's coming out, and getting bigger air bubbles to escape. This is the water transport by vibration. This is part of a study that was done by Peter Taylor at CP Tech Center. It's basically saying at 8,000 VPMs versus 12,000 VPMs, how much of the water was moved, causing it to become more permeable. The more blue, the more permeability that water is able to go into the concrete. Vibration frequency versus workability. We have a whole slide chart. It's for commercial. It's for regular pavement. Pavement is sitting here at about 8,000. We're kind of sitting in the 6,000 range where a lot of paving goes here by what the actual value of the slump is presently. And we work in this range for paving down here. But if you go below that bleed line, we talked about the relationship of frequency lubricating with a little bit of water separation. Well, you get below this line, you under vibrate, and you go over this line, you over vibrate, and up here you're just asking for a lot of trouble. So how vibration affects the carbon neutral initiative. In construction, there is a lot of emissions that are part of construction. We look at embodied carbon, and we look at what the vibrator means to cement use in mixture over designs that we talked about. Concrete production, is it uniform? How does it match the frequency that we're putting? Will it have durability issues, which is part of embodied carbon? Maintenance and repair, well, that's part of it. Like down the road, if we have a durability issue because of our relationship between vibration and the resistivity of concrete. What does it mean? And in the use phase carbon, the smoothness is important because of fuel consumption. If you get too wavy on the surface, it you will waste some emissions with your tires. So the next guy up, thank you very much, is Dr. Michael Ayers, president of the Global Pavement Consultants, Inc. And now here's Mike.
So thank you, Paul, for this nice presentation showing that the aspect of compaction and vibration is not always as easy as we thought. For the audience, I would like to ask you to write down your questions in the public chat. We'll wait till after the 3 presentations for a Q&A session. So it gives you some time also to think about the content and to ask the questions you want to ask. The second presentation will show us a number of cases of problems, remediations. We saw that a number of problems are possible. For instance, the entrained air which escapes, we heard about it, the poor aggregate arrangement, and so on. This presentation will be given by Dr. Michael Ayers. Mike is president of Global Pavement Consultants as a consultant. He is also executive director of the Illinois chapter of the ACPA, so the American Concrete Pavement Association. So we listen now to his presentation.
Good day, everyone. It's my pleasure to be here to talk to you a little bit about the effects of compaction in real-world scenarios. Paul has talked about the need for correct vibration energy, and I'm going to talk to you a little about the construction operations and what it affects if you have incorrect vibration. We're also going to look at remedial measures in case the vibration is incorrect. What can you do after the fact? Again, I'm Michael Ayers. I'm the president of Global Pavement Consultants in Fithian, Illinois, and I work fairly extensively worldwide in terms of construction operations and mix design for Keogh. So as an overview, Paul's addressed the issues regarding mechanical vibration energy, resistance to vibration, and the effects of vibration frequency. This portion of the webinar is going to focus on the following: mixed characteristics that influence the vibration required to consolidate the pavement, pavement distresses that are attributable to the lack of consolidation or over vibration, and finally, remediation techniques when pavement distresses are in evidence. We're going to look at a number of different types of distresses and what the standard recommended approach is. So why do we need to consolidate pavements? The answer to this is fairly obvious, but we're going to go through a little bit of the highlights of it from a practical standpoint. Depending on whether we have a jointed plain concrete pavement or a continuously reinforced concrete pavement, the need for vibration and the resulting consolidation varies somewhat. In the case of pavements when we have embedded steel, we have to consolidate the concrete around the steel in order for it to fulfill its design function, i.e. for dowel bars, we want a high level of load transfer efficiency fairly soon after construction, after the concrete is set up. So in other words, we can't have entrapped air, we can't have high water cement ratio under or over the bar. We need to have full encapsulation. The same can be held for deformed bars. If you don't have the concrete fully consolidated around the bars, they can't fulfill their design function, and the function of reinforced bars or deformed bars is to simply hold the concrete pavement together at the longitudinal joints, or in terms of CRCP, to hold the cracks tightly together. So consolidation is based very strongly on mixture proportioning. Consolidation needs are highly mix dependent, and that means that for a different mix consistency, different level of workability, we have significantly different vibration energy that needs to be imparted into the pavement. Ultimately, we're trying to get rid of entrapped air. We're trying to not blow out or diminish the amount of entrained air, and we're trying to get good consolidation around the steel if we have it embedded in the slabs. One of the most important things affecting vibration is the combined aggregate gradation, but also the surface texture of the particles and the particle shape are important because they somehow control or somewhat control the internal friction developed between the particles. The paste content relative to the voids of the combined aggregate is an important parameter. Assuming that we have an ideal gradation, we want to have the paste fill approximately 1.5 to 2 times the void space in that combined aggregate. Less than that, in order to consolidate it, you'd have to crank up the vibration energy to fully consolidate. If we have more paste than that, we have to back off on the vibration energy so that we don't have a tendency to separate out or segregate the concrete. The type and the amount of supplemental cementitious materials, i.e. fly ash, to some extent ground granulated blast furnace slag, that are present in the mix also have an impact. SCMs, for the most part, fly ash in particular, tends to be rounded, more rounded than the cement grains. So they act as a lubricant, and the higher the SCM content, the more fluid the mix is going to be for a specific water-cement ratio, all other factors being equal. When we put SCMs in the mix, we also have an impact on the carbon footprint. In the US, we're currently trying to lower our carbon footprint substantially. Our standard mix for many years has been 564 pounds of cement per cubic yard. We're trying to drive that number down substantially, down into the mid to low 400 pounds per cubic yard. The carbon imprint of that is going to be significant in pavement type selection, and moving forward, that is the direction we'll be taking. In addition, we also are switching to Portland limestone cement, or PLC. We have traditionally used type 1, type 1-2 cement. Now the only product that's going to be available to us, at least in the state of Illinois, is going to be PLC. We're making adjustments to our mixes to accommodate that, but there will also be resulting changes in the vibration energy necessary for consolidation. The presence of chemical admixtures also has a significant impact on the vibration, particularly water reducers, high-range water reducers, where we can lower the water-cement ratio to 0.38, 0.42, which is generally our target area, and we can pick up workability by virtue of putting in a water reducer. But that also directly impacts the amount of vibration required for a specific level of consolidation. So mix design, mix proportioning. The water or water vapor movement in concrete is basically through capillary pores within the hardened concrete. When we vibrate concrete, we essentially minimize the amount of capillary porosity. We also intend to minimize the amount of entrapped air while still maintaining a good entrained air content, both in bubble size and bubble spacing. Adequate consolidation can significantly impact the pore structure and therefore influence durability through controlling permeability. Concrete mixes can be engineered to be less permeable. We can do that through various additives. We can do that through the basic mix design process. We're in the arena now where we're looking at performance engineered mixes, and one of the criteria is going to be permeability as determined through resistivity. There are practical limits for reducing the concrete permeability through mix design only. Because we have cost elements that we have to be considering, and we also have material availability, which right now is somewhat of a challenge. The performance engineered or PEM mix approach is the most actively researched way to achieve these goals. We are continually looking for advancements in terms of testing protocols and how to characterize the mixes. But all of those things are going to have some influence on the vibration. But regardless of the mix properties, consolidation is required whether it's machine placement or hand placement. It is applicable whether or not it is 0 slump concrete or whether it is 5-6 inches of slump like we would use for a typical hand pour on a slab. So in terms of combined grading, this very much controls how much vibration we require for consolidation. What's on the screen is the tarantula curve. For many, many years in the construction industry, we have used the Shillstone chart for gradation. And that's, if you're aware of that way that we combine aggregates, it would give us a measure of workability that was desirable for slipform paving operations. For the most part, that Shillstone method worked, but there were enough exceptions that we went back and researched this, specifically Tyler Lay at Oklahoma State University, and came up with a tarantula curve for grading. There have been hundreds and hundreds of mix designs performed using this gradation, and the properties are significantly better. They're more controllable, they require less vibration for consolidation, and they promote uniformity of the concrete. All those things which we really desire. We can also use chemical admixtures that control the need for vibration energy. We are dealing, for the most part, with very low water cement ratios. So in order to achieve low permeability, while still allowing us to get a reasonable level of workability, we have to put in some types of admixtures. In order to facilitate that, water reducers, typically high-range water reducers as superplasticizers, are used. There are other products out there that do dual duty. The only one of those that I have worked with in the past several years has been the product that's on the screen, this International Chemcrete Multi-Crystalline Enhancer. Done extensive research with this product, and we found that if it's introduced into the concrete during the batching process, or after the fact, in the case of a transit mixed truck, you can add it on the job site. It significantly aids in flowability of the concrete. It potentially reduces the vibration energy required, and most importantly, it provides a large reduction in the concrete porosity and permeability, regardless of the level of vibration. So that product essentially crystallizes in the capillary pores of the concrete after vibration. So concrete distresses, as you're well aware, can be due to lack of consolidation, they can be due to segregation in mixes, they can be due to poor mix design, and a myriad of things. So what we're going to concentrate on the things that can be influenced by vibration. But keeping in mind that distresses in concrete pavements can be due to load, environment, design, construction, materials, and other factors. The carbon footprint of a pavement system, subgrade, subbase, slab, are heavily influenced by construction operations. The key element here being consolidation. In order to lower the carbon footprint of a pavement system, we can optimize the concrete mix design, but we can also optimize our construction operations. Because consolidation is so important in long-term performance of the concrete pavement, it will significantly influence the necessary remedial measures moving forward. So if you're looking at a life cycle cost analysis of a pavement, if you don't get adequate consolidation and you have distresses in the pavement, it simply reduces the lifetime of the pavement up till the point where the first, second, third rehabilitations occur. Every time that you have to go out and rehabilitate the pavement, you are expending more energy, hence carbon footprint goes up. So it is to our advantage to try to put the best mix design we possibly can and constructed correctly. This book was published several years ago, and if you don't have a copy of it, I would highly recommend that you click on this link and download a copy. It is multi-hundreds of pages long, and I wrote several chapters of this book, so I can tell you what is involved in it. We looked at what are the most typical types of distresses in every sort of pavement. Jointed plain, jointed reinforced, continuously reinforced. We have photos, we have a description of how to measure it, we have remedial measures that are recommended, but most importantly for what we're talking about today, it lists the potential causes of this. And you'll find as you go through this book, these 800 or so pages, many aspects of concrete pavement deterioration can be traced back to improper construction techniques. One of the biggest one of those things is the level of consolidation or vibration. Both under vibration and over vibration are both detrimental to long-term performance. So if you over vibrate a pavement, this is an example of a concrete pavement at an airport in Moldova. We did this project several years ago, and due to an over vibration of the concrete, because the concrete mix was not optimized, it was lacking in several elements to make it good long-term performance. But nonetheless, it was placed, consolidated, and finished. The first season where freeze-thaw damage occurred, the vast majority of the airport experienced this type of distress. Well, because of the FOD that's generated, you really can't operate flights on this because the opportunity for this stuff flaking off to be ingested into the jet engine. So this is a bad situation. Could we have done anything differently in vibration? Absolutely. This is another type of distress that is somewhat relative to vibration energy. Delamination occurs when the upper concrete surface is, generally speaking, at a high water cement ratio. We over vibrate the concrete, we sink the coarse and intermediate size fraction aggregates, we bring paste to the surface or mortar to the surface. That surface is friable because it generally has a low water cement ratio, but it's been offset by having water introduced into the system and by simply removing air content during the vibration process. It's an important distinction to make. What happens? This is a photo of over vibration. What you see where the red arrow is the path of the vibrator. The vibration energy was so high that the particle interaction was poor, and it simply settled out the coarser size fractions of aggregates, and it brought nothing but mortar and paste to the surface. This is not a long-term durable solution, and this will directly impact the carbon imprint of the concrete pavement for the long term. So this is an example of that same airport project. Not only was the surface friable and scaled off, it was also very porous. What I did is took a bottle of water and poured it on the surface. Almost instantaneously, the surface absorbed the water that I'd placed on it. Now you can look ahead and say, well, if that is the case, then this pavement is going to absorb water at every rainfall event, every snow, every ice event. And because water expands roughly 9% in the porous structure of this concrete, it's going to continue to scale. And so we had to do some remedial measure that we'll come back to in a second. If you look at that pavement, there's distinct vibrator trails. That's what the arrows are pointing at. Those areas are the ones that are scaling off and the most friable. If you looked at the close-up photo of this, you would find that every vibrator trail has very significant scaling and delamination at the surface. So the question becomes then, what can we do to fix this? It's simply not feasible in most cases to remove and replace. So what are our options? Well, there are also non-surface issues that come from poor vibration. There's lack of consolidation causes voids in the pavement structure. I'm a pavement designer besides being a materials guy. So as I look at this, what it speaks to me is that that area of the pavement is going to be less structurally able to carry the loads that are imposed on it. I'm going to get premature deterioration. If that's widespread, it's a mixture problem that maybe or maybe not can be compensated for with vibration. But the first thing I'm going to do if I see that is I'm going to go back and I'm going to re-engineer the mix. And the second thing is I'm going to look at the machine setup and the amount of vibration energy required. So this is our go-to when we have surface deterioration. We simply grind the surface. Well, grinding the surface by itself most of the time is going to be sufficient, but there are many cases where that is not the case. If you go back to that picture that we just looked at with that high level of porosity, you diamond grind the surface of that, and because it goes down beyond the limits of what we're going to grind, we just can't compensate for that level of deterioration that we're going to anticipate. So the diamond ground surface looks like this. The question to ask when you're doing an evaluation after the fact is that surface sound? Is it still prone to scaling? And is it permeable? Well, in this particular case, because there was so much friable surface and it went down almost an inch, we came back after the fact and sprayed application of a sealer on the pavement because we have to eliminate moisture intrusion into the slab. So now we have this driven by vibration. We've ground it, but we still haven't solved the problem. So it required the addition of this sealer. This is O'Hare Airport. We did this job in 2020. There's 1 million square feet of airport pavement that had a friable surface. There were areas that were obviously distressed, and we fixed those by diamond grinding. But we didn't have any avenue to fix the porosity problem, which was widespread because of the mix design and the construction operations, specifically vibration. So we came back and we sprayed the entire 1 million square feet with this product that soaked into the concrete and made the surface totally impermeable to the ingress of both water and chlorides, which they use in this airport. O'Hare Airport is, as you know, a huge facility, one of the world's most busy airports. You cannot take it out of service for long. We were able to spray apply this on the entire 1 million square feet in 2 days. The results, 2 years, coming on 3 years later, have been outstanding. There has been zero additional surface deterioration after we applied that and we did the limited diamond grinding. So the options are, again, and I want to throw this out there because these products are something I work with a substantial amount and I know for certain that they work. This Pavix from Chemcrete Company, CCC 100, unique patented dual crystalline penetrating sealer. That's what we applied to O'Hare. That's what we applied to Moldova Airport. That's what we applied to pavements worldwide. We've always had outstanding results if it's done correctly. The other product we previously talked about is the MCE multicrystalline enhancer that can aid flowability and reduce the vibration energy required for adequate placement and consolidation. But perhaps an even better use of that is it limits permeability. So even if the vibration is incorrect and we do have capillary porosity more than we'd like, the MCE will fill in the voids and make the pavement almost totally impermeable. So the multicrystalline enhancer, there's a lot of benefits of this product in addition to what I've talked about. But essentially you mix it in with the fresh concrete during the time of batching, you place it, and then you can turn down the vibrators because it does aid so much in flowability. You can use it at both central mix and ready mix plants. And with that, I am going to turn it over to Rory, and he's going to speak to you in terms of the effects of equipment setup and the new innovations in equipment. Thank you very much, and we'll be available afterwards for questions and answers.
So, thank you, Mike, for this great presentation, showing us some of the distresses we can have due to over or under compaction, and also offering us some of the solutions. Let's go directly now to the third presentation, which will show us the practice of slipform paving with an Auto-Vib system. The presenter is Rory Keogh. Rory is Managing Director of Keogh International, but Rory is also Vice President of EUPAVE and also Chairman of our Technical and Promotion Committee. So, Rory, we'll listen to your story. Thanks.
Hi everyone, and welcome to EUPAVE's webinar on concrete compaction. My name's Rory Keogh. I've been recently retired as the Managing Director for Keogh International after 38 years. I'm now functioning as a consultant. In addition, I'm Vice President of EUPAVE and also a Director of BritPave. My presentation today provides a slipform paving manufacturer's overview on how a manufacturer is working with the concrete industry in developing a controlled vibration system to monitor and react instantly during a paving operation. Both Paul's presentation highlighting the importance vibration plays in a paving operation, plus the applied vibration against concrete mechanical resistance and its impact on carbon neutrality, and Mike's mixture characteristics that are influenced by vibration consolidation. The common theme in all of this is the control of vibration. If you control the vibration frequency in the concrete, you can begin to concentrate on other variabilities. Vibration energy is measurable and its effects on concrete are quantifiable. Vibration energy and the mechanical resistance of concrete needed to be balanced to limit distresses from material separation. The variances from the processes in the concrete workability system need to be measured in real time to reduce carbon generation from field practices. Vibrator characteristics. A concrete vibrator produces force at a certain frequency. The energy cannot be evaluated with a simple linear representation or vector because of the way the vectors are dispersed in the irregular particles that consist in the concrete. Controlled vibration energy has to be quantified by speed and force and empirically applied to the mixed viscosities. The near solid concrete is liquefied, reduced viscosity, during vibration and returned to a solid once the vibration stops. Vibration is meant to extract micro air, somewhere around a millimeter diameter, and leaves the concrete in a uniform state that it was placed. On this slide, the variation, energy and concrete's workability needs to match. The slide identifies the areas of variability that confronts the contractor once the mix design has been determined. The constant, which is the materials, then gets placed into a batching plant. And this is where the materials, the moisture within the material has to be measured before the water is added, and then you have the various additives that you would put in. Once this has been achieved and the mix has gone through its cycles, it's then placed into a vehicle, either a transit mixer or an end dump truck, to be delivered to the paver. Now the variability it comes in this operation, depending on the distance from batch plant to paver, the quality of the road it's running on, to avoid creating additional segregation, and also the ambient temperature. I'm showing here a triangle with the three important elements in a paving operation, which is paving speed, vibration frequency in relation to paving speed, and concrete slump. Here we're trying to establish how much time the vibrator is in contact with a cubic meter of concrete. Measuring energy in a cubic meter of concrete while being vibrated internally. A slipform paver drags a vibrator head at an average speed of around a meter to 1.2 meters per minute. This equates to the cubic meter of concrete being in contact with the surface area of the vibrator for around 10 seconds. Now, if the paver slows down, the vibration frequency does not get adjusted. Therefore, the time the vibrator spends vibrating the same area of concrete can easily cause a degree of segregation. The more the vibrator speed, the more damage during that period. And it's quite normal for pavers to adjust the travel speed or the paving speed, but not adjust the vibrator frequency. These two slides identifying vibrator trails. The arrows are highlighting an area where the vibrator trail has started to develop a longitudinal crack. And as you can see on the left picture, there's a lot of cracks appearing, all longitudinally. Similarly, on the right, this slab is an airport apron, and we've got two variations. On the top left, you can see black arrows identifying vibrator trails, and down the bottom part, you can see the surface has started to crack up, which has occurred within a year of the airport pavement being open to traffic. On this slide, the top left shows the effect of too little vibration. The pockets of air are trapped in the concrete, creating honeycomb effect, makes the slab brittle. One element again to the low vibration would be to slow the paver down and also to speed up the vibrators. The picture on the left with the red arrow is showing effects of over-vibration where the aggregate separates, leaving a section of concrete with no aggregates interlocking. And I've got a photograph here in the middle where water is identified, and even with very dry mixes, to get the mix fluid workable, you have to increase the vibration frequency to the point where you will draw water and it invariably comes to the surface, leaving a film of slurry, and in due course you will end up with surface cracking. Some further results from cores that have been taken on slabs that have come to the end of their life early. The slide in the middle shows a number of little potholes, and this could be as a result of impurities in the mix design, or maybe clay's been left in there. My final slide showing cores, this identifies the optimum consolidation in the slab, where you've got evenly distributed aggregates all interlocking without segregation. Now, to achieve this on a consistent basis, you have to be able to control vibrator speed and paving speed to match the mix design that is put in front of the paver. Moving on now to the vibrators and the various methods of testing the frequency. The traditional tachometers for measuring frequency, I'm showing 3 here. The middle one is the pencil, the least expensive and the least accurate. The one at the bottom is the reed tachometer. It's the middle of the road and has been a standard in the industry for many years. And at the very top, we've got the digital tachometer, most expensive, but the most accurate. It can also be used for testing the Auto-Vib sensors. In order to create a more predictive vibration model, an automatic vibrating monitoring and control system needs to be developed, and in order that it can be fitted to a slipform paver. Now, the functions of an Auto-Vib system: you get a programmable VPM set point, convenient vibrator speed adjustment, a programmable set point on ground speed for automatic control of vibrators. For this, you'd need to make sure you've included the speed option, real-time readout, a VPM readout of vibrators. You get an alarm which you set for high and low frequencies. You get a display showing the centrifugal force, and then on the optional side you get a monitoring system for temperatures and for ground speed and distance travelled. This slide is showing the components that make up an Auto-Vib 3 package. At the bottom right, you've got the valve bank, which consists of 10 sets of 10 vibrators. On the left, you've got the censored vibrator. It's possible, or some models out in the field, to upgrade them to an Auto-Vib system. It does require changing quite a lot of the hydraulic system and replacing the valves. The vibrators can be upgraded with a sensing system installed. Here we're identifying the Minnich controller, which stores the data and then feeds it to the Gameco navigator as a display system. This is identifying the G+ navigator monitoring system, which you'll be able to control the vibrator frequency in relation to the travel speed. As the paver slows down, so should the vibrators to prevent over-consolidation. As the paver speeds up, so should the vibrators to prevent under-consolidation. You would also, when you set the maximum and minimum paving frequency, vibration frequencies, if for any reason the vibrator goes outside of those, the color in the slots would change, and you can decide which colors you want, but it brings to the attention of the operator and the supervisors instantly that you've got a faulty vibrator out there. The Auto-Vib system comes in 2 levels. The introductory and basic system is Auto-Vib 2, and then the top end is the Auto-Vib 3. The Auto-Vib 2 is purely a feedback and monitoring system. It provides a feedback system delivered to the Minnich data box that's clamped to the railing of the machine. It then delivers or transfers that data across to the navigator, which will show you all the graphs. But all the data on an Auto-Vib system is stored in the Minnich controller. There's no data stored on the Gameco side. We only display the graphs. The feedback is communicated from the Minnich via CAN line to the navigator. The Auto-Vib 3 has all the same features and functions as the Auto-Vib 2, with the extra components added on by Gameco. Each vibrator has its own proportional valve, as well as an independent feedback, which works through a closed-loop drive system, so it can be adjusted independently. You could set your vibrators in the middle of the pan at, say, 6,000 VPM, and the ones on the corners set at 6,500 or even lower at 5,500. The system will take into account the temperature of the hydraulic oil and always be at a set speed. It will also take into account the wear on any hydraulic motor to account for the extra oil loss, so it will maintain the speed. The programmable set point on the ground speed and automatic control of vibrators does require the ground speed option to be added. adjustments to the navigator can shut down one or all the vibrators at the same time, as well as you can adjust one or you can adjust all 10 on a bank at the same time. If you have different speeds selected between the vibrators, all your adjustments keep the same ratio as you move them up or down on the frequency scale. You can also equip the navigator with a wireless kit, and that's allowing you to have several monitors, tough book monitors on the paver, and it allows then for a number of staff or people on the paver to monitor the vibrating system as you're paving. The navigator, as I said earlier, also has warning colors so that you can set them up and the lights will flash when the vibrators move out of sequence. What I'm showing here is once you've established the area of influence of the vibrator, you've got to ensure that when you set the centers, you make the correct adjustment for an overlap. The overlap is the key to your consolidation and improving the consistency of vibration across your slab. And this proves the point. The top line shows you the variations in area of influence, and this is very similar to a standard system where the vibrators, although you set them all at the same frequency, due to various wear and tear on the internal elements of the gears in the vibrator or the valves in the valve block, the oil flow is restricted, and as a consequence, your area of influence gets affected. If we introduce the Auto-Vib 3 system, it will show you a consistent area of influence on each vibrator as shown in the bottom line. Finishing off, here I'm showing you a set of vibrators on the mould of a slipform paver, all set parallel to the surface of the concrete. And this allows you to pave over blockouts. When you're not paving over blockouts, it's important the operator adjusts the vibrator angle hydraulically and lowers the tip of the vibrator into the mouth of the mould, ensuring that you're getting better vibration areas of influence going through the mouth of the mould. On the left side, the drawing of a typical slipform mould is showing you the various adjustments to the vibrators depending on the thickness of slab you're paving and whatever is set out in front of the paver. So you can lower if you're paving a 600mm slab, you can lower the vibrator to 300 to give you all the consolidation you want. If you're paving a 220mm road slab, you can raise the vibrator, and if you're paving over blockouts, you can raise it to above the roof of the mould. Off, at the end of your day's paving, all the data is being collected from the vibrators, the frequencies, the paving speed, the stops and starts. It's all registered, and you download it onto your phone app or onto a memory stick, and you're able to sit down at the end of the day and analyze it on a laptop. Thank you very much for listening, and any questions, please let me know. Thank you again.
So, thank you, Rory. You showed us how, in practice, vibration can be monitored and controlled. For our participants, one more practical communication. There was one question, and yes, indeed, the recordings of the presentations will be made available to all participants, so you can look at them afterwards again. So now it's time for some questions. We had some questions in the chat. I also have some questions for our speakers. So for the first speaker, for Mr. Paul Jaworski, we had a question from Kelvin, who asked, how long should you vibrate a concrete slab for? I think it's not an easy question. I don't know. Paul, are you there? Can you give us a reply? And I also have the other question, another question about the V. Kelly test that Paul has presented. So my question is, if that test is generally applied, I have to admit, in Belgium we still use the Abrams cone. In the past we used the VB test, but the V. Kelly, yeah, maybe better. Seems a bit more complicated. But so, is this more generally applied in the United States? In the meantime, I see that also Mike replied to the question of Zach about the amount of acceptable voice in the core. Of course, yes, it varies by the agency. Small voice are usually accepted. Yes, I have the same experience, but indeed, larger interconnected voice will affect durability. Will also affect mostly concrete strength, whether it's compressive strength or flexural strength. There is also a question of Elia, who says, well, there are differences between the concrete mixes in the United States and in Europe. So does it mean that we also have to adjust the vibrator frequency, the technique, and are there any guidelines to do so? That's also a question for Mike, I thought. Oh, the question to Mike and to Paul, if they can reply in the public chat, so then we can see the replies. If we don't get them now, of course, we will provide them afterwards. I also have a question for Rory about the Auto-Vib system. Seems really performing. So my question is also, how generally is it used, or most of the Slipform pavers equipped with this or not? Is it sometimes maybe prescribed in tendering documents, or is it more left to the appreciation of the contractor, who will then be able to provide a higher quality, but of course also for a higher price? Indeed, and so Mike replies to Elia that indeed, if there are differences in concrete mixes, so then vibration is dependent on that mix design and requires some adjustment. While Rory says that the Auto-Vib is offered as an option, yeah, that's also what I was thinking. But it's a good option, I believe, because it gives some possibilities to monitor. So the question is, shouldn't it be in some tendering for large projects, shouldn't it be imposed? And also a question that also often comes up, yeah, what about the electrically driven vibrators? So Mr. Ayers also responds to earlier that the key elements are the combined gradation, water cement ratio, and the paste voids ratio. To some extent, I believe that they will be different between Europe and the United States. We also heard Mike saying that they're going as low as to something like 400 pounds a cubic yard, which is around 240 kilograms a cubic meter of cement, way lower than what we use in Europe, especially in Belgium. So then also the question is, yeah, do we get to the same strength? And what about the thickness? Because of course, yeah, we're going to go to lower binder contents, lower thickness, but and maybe lower strength. But if you have to compensate it in thickness, yeah, we will not really gain in carbon footprint. So we see in a chat, Rory continues on the Auto-Vib system, telling that there are many contractors looking to improve the quality purchase, and they purchase the systems. Yes, of course, those are the ones we need. And Mike will look for some guidelines and will send it to Elia. So that's great. Are there any other questions? I think most of them have been answered for the moment. If not, we still can do this afterwards. I believe we can come to the closing remarks of this webinar, Optimal Compaction for a Durable Concrete Surface. I think we learned about the importance of the compaction of a concrete pavement. We understand that in order to get a sustainable and a low carbon pavement, that is only possible with a durable pavement. So there are a lot of, and also a durable surface showing no distresses. There are very many design and construction parameters that play a role. And now we understand that compaction is a very important parameter that should be monitored, should be controlled during paving. I thank you all for joining us at this webinar. So, for those who are interested in the heavy-duty pavements and the industrial pavements, so don't forget to register for our next EUPAVE workshop on best practices, which will take place in a hybrid form on the 19th of April for the European, especially the Belgian colleagues. It's also possible to attend in person in Brussels in the FIBELSEM and EUPAVE premises. So, thank you all. Have a good day. See you later. Bye.